Hello and welcome to Empowered Learning. This particular video will be on the study of the logarithmic function and its relationship to the exponential function. If you have not already done so, I have videos on exponential functions and graphing. So if you don't know what an exponential function is, or if you need to get a refresher on that, please watch that video first before watching this one. So in essence, when we start to talk about exponential functions, we can't talk about those without actually talking about a logarithmic function. And so what I have here is a graph of a basic exponential function as well as a graph of a logarithmic function. And so the basic relationship in between a logarithm function and an exponential function is that they are what we call inverses of one another. Okay? And so what we mean by an inverse is that if we can take the graph of one of these functions and interchange the x and y values, in other words, flip them around and then draw that graph, then that result would end up being the inverse. But it's only special type of functions that can do that. And so functions that are considered to be what we call one-to-one functions. And so one-to-one functions are functions that only that have, for every x value that they have a unique y value to go with it. To give you some more basic examples of what I mean by that, let's look at the function y equal to x squared, and we're going to look at the function y is equal to x cubed. Okay, so the function y equals x squared basically looks like a u, so our basic parabola. Our function y equals x cubed looks like this. And so what we mean by a function being one-to-one from a graphical standpoint is that it passes what we call the vertical line test and the horizontal line test. The vertical line test says that I can draw a vertical line anywhere in the graph that I'm considering, and if a vertical line intersects at most one time at any place I draw it, then I know that the graph that I have is a function. So for x cubed, if I do that, you see that I know that x cubed is indeed a function. The horizontal line test says that if I draw a horizontal line anywhere in my graph, and the maximum amount of times that any horizontal line crosses the graph is once, then I have what's called a one-to-one function, meaning that every x value for the points that I have on that graph matches up with a unique y value. Okay, so x cubed does follow that. So we know that x cubed is what is considered to be a one-to-one function, meaning every x value has its own unique y value to go with. X squared, however, does not satisfy both of those conditions. We know that x squared is a function because it passes the vertical line test, but it does not pass the horizontal line test because we see for this horizontal line, it crosses x squared both here and here. So x squared is not considered to be a one-to-one function. Okay. Now, I'm going to erase all of this and go to our actual graphs here so you can see how that relates to what we're doing here. So let's take the graph of a raised to the x, which is our basic exponential function. If we draw vertical lines through it anywhere, we see that all those vertical lines only intersect the function once. So we know that y equals a raised to the x is a function. Okay. Now, if we do it horizontally, we see that our graph also is only intersected by the horizontal lines once, okay, for any given horizontal line that we draw. So we know that a to the x is what we call a one-to-one function. So, and because of that, what we know is the following. I'll go ahead and put the key points that I mentioned in my previous videos here. Of course, we know that -1, 0, 1 we have 1 over a, 1, and a. So for every x value that we see, we have a unique y value that goes with it. So we know that 1 over a is going to be different than 1. 1 over a is going to be different than a. So all these x values have a unique y value that it goes with. Okay. Now, in essence of what we're talking about here, if you notice, we have these 3 points, which is -1, 1 over a, 0, 1, and 1a. Okay. For the logarithm function, because the exponential function is a one-to-one function, we can interchange the x and y values, meaning that we can flip these. So if I flipped the x and y values, then what I would have instead here is 1 over a, -1, 1, 0, and then a, 1. Okay, and if you notice here for this graph, there's the 1 over a, -1, the 1, 0, and the point a1 right there. So if all we do is just take these values and flip them, then we can produce the inverse graph of the exponential called the logarithm. Okay, and if we know this, the logarithm will pass the vertical and horizontal line test as well. Okay, and so because of that, these two functions are inverses of one another. To get a deeper explanation of inverse functions, you can watch my videos on that as well. Okay, but for right now, that is the basic relationship in between the logarithm and the exponential function. Okay, now because of that, there are a lot of things that we can do because of this relationship, and one of those things is being able to take an expression, or an equation rather, that is in exponential form and translate it or transform it into a logarithmic function, and vice versa. Okay, so and that's towards the end of this particular video, that's the kind of things that we're going to be doing. For right now, what we want to do is just get familiar with how the graphs of these functions are going to look. Okay, and so down here I still have key points again. If -1, 0, 1, 1 over a, 1, and a, we know that these are the key points for the exponential. For the logarithm, we just interchange all those around. And of course, the domain of the exponential function ends up being the range of its inverse, and the range of the exponential ends up being the domain of the inverse function of logarithm. Okay, and so that's the other special type of relationship that we have once we know that two functions are inverses of one another. The domain of one function is the range of the inverse, and the range of one of those functions is the domain of the inverse. Okay. All right, so some simple examples here. Now that we know what the logarithm graph is and how it is related to the exponential, we're going to go ahead and do just like how we did with the exponential graphs, use our key points to be able to draw a sketch of what the logarithm function looks like. And so in this instance, we know that log base 2 of x, the key points for this is going to be these points here. And so one of the things that I recommend is that if you don't want to memorize the logarithm key points and the exponential key points, one thing that you can do is just memorize the exponential key points, and then just know whenever you're dealing with a logarithm, you need to flip those x and y coordinates. So to show you what I mean here, I'm going to come and actually I'm going to increase this to make this a little bit bigger. I'm going to write let's see. I'm going to write what the base function would be for 2 to the x here. So if this is 2 to the x, which is the inverse function for log base 2 of x, it would look like this. Okay, so here, if you notice, I have -1, 1/2, 0, 1, 1, 2. If I go from here straight to here, you see that I have the exact same thing, but it's just flipped. Okay, so if you can know that log base 2 of x is inverse function is the exponential 2 raised to the x, you can just do that and then flip those values and end up with the same thing. Okay, so that's an alternative way of looking at it here. All right, so anyway, for example A, we see that for log base 2 of x, we have our key points, whether you want to do it by flipping the exponential or just memorize what the key points for the logarithm are, and then you just plot those points and you graph. Okay, now I'm going to go back one page here. If you remember, whenever we were dealing with the exponential function, we had a horizontal asymptote at y equals 0, okay, telling us that our exponential function cannot go below the x-axis here. For our logarithm function, since we are flipping everything, if we take our horizontal asymptote and we interchange it or flip it, that horizontal asymptote now becomes a vertical asymptote, and that is expressed here by x equals 0. So my point is that for the logarithmic function here, instead of having a horizontal asymptote at y equals 0, which is the x-axis, it has a vertical asymptote at x equals 0. Okay, and so we know that for those type functions, the logarithm functions rather, we cannot have x values that are negative or 0, which means that x basically has to be greater than 0. This logarithmic function will never cross the y-axis, which is what x equals 0 represents. Okay, so saying that, to say that in this graph, if you look at log base 2 of x, do you see how it gets really, really close to the y-axis, but it never crosses? Well, the reason for that is because we have a vertical asymptote here at x equals 0. Okay. All right, similarly, for example B here, we see log base 5 of x. Of course, if we wanted to figure out what the key points of 5 raised to the x were, we would just do these and then flip these to get the ones for the logarithm. Okay, same kind of deal though. Once we have our points, we just graph it. We know that the basic profile is going to kind of from right to left kind of do this and slant down, and as we get closer and closer to the y-axis, it starts to ride along there but never touch or cross. Okay, and again we have a vertical asymptote here at x equals 0. Okay, so for example D, we see we have what's called log base e of x, and in short we call that natural log of x, and so we'll see that later, but log base e of x is nicknamed natural logarithm of x, and again e is a number that's approximately equal to 2.71, and that didn't come out right, so let's try it again. Okay, and so for here, again, we could do the same thing, e to the x, do our key points here. And so we would have 1 over e, 1, and e. And so if we just flip those around, then we get what we see right here. And so we can take that and graph it as well. Okay. Of course, you could take e, put in your calculator, do 1 over that, and figure out what that is. It would probably be about 0.48 or something like that. And of course, e by itself is approximately 2.71. So that's how I'm estimating where these points are. And again, remember that we have a vertical asymptote at x equals 0. So that means that the logarithm function cannot cross or touch All right, so example C we will do on our own here. So I'll take the approach of doing 10 raised to the x. So negative 1, 0, 1. That would be 1/10, 1 and 10. So that means that log base 10 of x. And of course, log base 10 of x is just written as log of x. So on your calculators, if you see this button that just has log on it, that is interpreted to be log base 10. And so log base 10 is the most popular base that we use because we count everything in tens. We have 10 fingers, we have 10 toes. So we do everything in powers of 10. So that's why for this one, when we just say log base x, we really mean log base 10 of x. Okay. So for here, we know that 10 raised to the x and log base 10 of x are inverses of one another. So we just need to flip the corresponding points there and look like this. And so if we plot these points, we have a negative 1, 1/10 negative 1. So that would be about right here. We have 1, 0, which is there, and then we would have 10, 1, which is there. And so, of course, if we were trying to draw this, it would look something like that. Ooh. Yep, didn't mean to cross that, so I'll try that again. That didn't work either. So something like that, get close, but never cross. So something like that. Okay. All right. And so 1 over e, yeah, I have it down here. It's actually equal to 1.367, blah, 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 blah. Okay, not 0.48. So, all right. So looking forward here, now that we have the basics of what a logarithmic and exponential function are in its relationships, the next thing we need to talk about is converting equation-wise from a exponential to logarithm, logarithm to exponential. So logarithmic functions are special because they are inverses of the exponential. So we've already talked about that. And so because of that relationship of being able to interchange the x and y values and switch from exponential graph to logarithmic graph, from an algebraic perspective, we could do this by taking, let's say, a logarithmic function and switching it to an exponential and vice versa. And so the easiest way to look at this is to look at the log version of an equation here and say to go from a logarithm to an exponential, we just say a raised to the y is equal to x. Again, a raised to the y is equal to x. A raised to the y is equal to x. When we go from this form back to the other form, one of the things that we want to remember is what a logarithm actually represents. And so to do that, I'm going to go back to our original graph here and say that whenever we are plotting the logarithm, what the logarithm is, it is just our way of tracking the exponent for an exponential function, okay? And so to make my point here, I'm going to go to one of these examples here. And so let's take example A, okay? So I'm going to erase this part and erase that and erase that. Okay. So what we're saying here, if we had 2 raised to the x, we know that x is going to be the actual exponent here, okay? But if you notice in the logarithm, what x is what y actually is over here, okay? So when we say a logarithm, we're saying, hey, give me the exponent for an exponential number that has a base of 2 and its result is 1/2. Okay, so when we say the logarithm, well, we're essentially saying something like this. So I want to know 2 raised to what is going to give me a result of 1/2. And of course, we know that if we stick a -1 in the box, then that's going to be what the answer would be. Of course, here we know 2 raised to what is going to give us 1. That would be 0. And here we know that 2 raised to what will give us 2. In that case, that'll be 1. So that's why in this box we would see a 0. We would see, sorry, in this box we'll see a -1. In this box we'll see a 0. And in this box we'll see a 1. Okay. So understanding that, we know that the logarithm is nothing more than a fancy way of expressing the inverse, the exponent of an exponential function. Okay. And to make that point again, if we look at these two forms, notice that we see y right here. Okay. Y isn't the exponent of the exponential function, but y is actually equal to all of this stuff. Okay. So that's why we say that the logarithm is nothing more than a fancy way of expressing the exponent of an exponential function. Okay. And so this rule of taking, let's say, y is equal to log base a of x and transforming it to an exponential function equivalent by going a raised to the y is equal to x, this is known as the definition of a logarithm. Okay. And so again, logarithms are nothing more than a fancy and useful way to express the exponent of an exponential function. And so now to do the conversions here, we see that if we take this exponential function, for example, we can transform it into a logarithm by noticing that 2 is the exponent, so that's what y would be. We know that the base for the exponential expression is 5, so that would be the same base for the logarithm. And then, of course, the result here would be what's inside the parenthesis there. Okay? And so to check it, we can always go the other way and say a raised to the y is equal to x. And so in this case, 5 raised to the 2 is equal to 25. That makes sense, so it all checks out. Similarly, if we have exponential equation 2 raised to the power of 3, which is equal to 8, we know that that's true to write this in logarithmic form or writing it as 3 is equal to log base 2 of 8. And so when we write it like this, we're actually saying 3 is the exponent for the exponential function that has a base of 2 and its result is 8. Okay, so what will go in the box here is the 3. Okay. Now, other example, e raised to the 0 is equal to 1. This is how it would look if we wrote it in logarithmic form. And of course, log base e, we've talked about that, is nicknamed natural logarithm of x. Okay. And for our next example, we have 10 raised to the 2 is equal to 100. So in logarithmic form, we know that that would be 2 equals log base 10 of 100. So our base here is 10. Value for y, which is our exponent, is 2. And our result is 100. Okay. So now converting the other way, going from a logarithm to an exponential, this way is actually easier to do because now all we have to do is say a raised to the y is equal to x. And so a raised to the y is equal to x, 4 cubed is equal to 64. Okay. Again, a raised to the y is equal to x, 2 raised to the 4 is 16. Okay. And so again, to reiterate, log of x really means log base 10 of x. Natural log of x really means log base e of x. And our most common bases that are used are 10, e, 2, 8, and 16 in that order. Okay. And so one of the reasons why we use logarithms in general is to take numbers that are very, very large or very, very small and refer to them in terms of the exponent of that number instead of just the number itself. So for instance, the Richter scale. The Richter scale, when we say a 4.0 on the Richter scale, what we are actually saying is that the earthquake that was detected was about 10,000 times more powerful or more intense than the smallest detectable tectonic plate shift that will cause an earthquake in the first place. Okay, and of course, 10 raised to the 4 is 10,000. Okay, so when we say 4.0 on the Richter scale, we're actually referring to this exponent right there. Okay, if we did not have logarithms, we would have to say that, all right, we had an earthquake that was 10,000 times more intense than the smallest detectable earthquake. And so every time they would mention that, they would have to do that long sentence. And so, of course, to just make that a little bit more succinct, is we just do a logarithmic scale and say, all right, well, we know what 4.0 is. Of course, if we had 9.0, then that would be about 1 billion times larger than the smallest detectable earthquake. And of course, there's a big difference between 10,000 and 1 billion. So you can see why 9.0 on the Richter scale is a much more serious situation than 4.0. Okay. All right, so anyway, last part here, the conversion of nth roots. So from the radical expressions, videos that I've done, I've stuck this in here because we're going to have to use this to be able to solve some of our logarithmic equations later on. Okay, so just want to make this mindful here to everyone.